Okay, today we're going to be talking about system modeling. It's an exciting topic. I have a couple of actual examples of a system model. Last week when we talked about the Teamwork Thursday stuff, and I said I was going to talk about the SunSwift race because it's an interesting story. I realized that there's actually an example of this that we can go through today, so we can actually learn about some of these things in the context of um, system modeling, which I think is very exciting. So, getting into it, what in the world is system modeling? Because that sounds like a very boring topic, right? Essentially, there's this critical part of software design that's being able to translate complex ideas or complex systems into something high level and understandable. The main things we're going to be talking about today are conceptual models, which are a type of system model, and state diagrams, which are a type of conceptual model. So this is a big, broad umbrella of topics, though we're going to focus in on a couple of key things. Now, what is a model? Many of you probably have different ideas when you think about model, right? You have the very off-topic idea of a model, someone who dresses up, but if you're thinking on the right track, which many of you are, you probably think of one of two things. Either something that's like a model, a mathematical model, or like a model of an atom or something, because you would have learned about models in science, or like a model aeroplane, right? Like I have a thing in my drawer somewhere that's like the beginning of a model aeroplane that I haven't gotten around to build yet. But you have this is like the parts for a little aeroplane that you take out, and I started building it, right? So you have these little models, and I don't know. Yeah, this is all I've done of it, right? It's just a little thing. So that's like one idea of a model that many of you will be familiar with. Then you have the kind of the abstract models like the thing of the atom. And what's interesting about today is that we're really focusing on conceptual models, and conceptual models are models that are they capture things in a conceptual way. So it's not what I just showed you there. While that is a model, it's not what you would call a conceptual model, right? It's a physical model. It's a two-scale physical model. So conceptual models are a way to model a system where we try and capture something very complex, and we try and do it at a high level and make it a bit more diagrammatic or visual, generally speaking. Sometimes they don't have to be diagrammatic or visual, which we'll talk about later. Though in general, it's a high level abstraction of a complex system. You would have heard the phrase weather model, for instance, right? A weather model is just a way to take weather, which is a very complex thing, and reduce it down to a high level. Here are just the key things. We just have sunlight and input and everything else, and we'll talk about weather again later. In terms of conceptual models, we care about lots of different kinds of conceptual models, and many of them you'll continue to come across throughout your degree. For instance, we have data models. Typically, these are in the form of what we might call like an entity relation diagram or ER diagram. You learn about these if you go to databases, which I think is Comp 3311, a course I'd strongly recommend. You've got mathematical models where you actually try and model something mathematically. An example of that is a lot of stuff to do with finance. As an example, at the moment, I'm trying to do some work away from UNSW around trying to figure out how much a product will make money and cost money, right? You're trying to model the complex behavior of humans in marketplaces and actually reduce it to something simple that people can understand. The more people that do this, the more money, that kind of thing. You have domain models, which, there's, these are all just different names for things, but there's a lot of domain models that you'll see in the form of class diagrams, and I've kind of omitted these, I think, today, but you learn this in 2511, where as you try out a different type of programming, which is object-oriented programming, there's a certain way where you can try and model different classes. And on the topic of classes, Jake is taking the first hour of the lecture tomorrow to actually give you a kind of a quick crash course on Python classes. So there's an entire world about how to draw out your program in that structure. And then one of the most important ones is state transition models. This is the one that we chose to talk about in this course because we don't do enough data modeling. We don't do enough class diagram modeling. And what you're doing here that you wouldn't have done in like Comp 1511 is have a sense of state. Because if you remember back to Comp 1511, generally speaking, it was like, here's your program, it runs, it stops. Whereas what's cool about your project and what's cool about a lot of systems we look at, particularly once we start getting into like Flask servers, is that if you think about your project server, it essentially moves between a series of states, you know. Starts here, no one's registered, then people have registered, then, you know, etc. And that's what we're going to be talking about in a bit more detail. How are models used though? Or like, you know, why they used might be another question that's relevant here. Like, why do we want to draw state diagrams? Why do we want to do data models? Why do we want to do mathematical models? And pretty much the answer is always the same thing. It's either we want to understand the past, we want to make sense of the present, or we want to predict the future. You know, and quite often it's for predicting the future. In the kind of practical sense, typically what you'll do is you'll build a model that you think captures how things work now. You'll then go and see, if I apply this model to the past, does it work? Does it make sense? And then if that makes sense, it gives you a sense that this can probably be applied to the future, right? And in a lot of ways, that's kind of the foundation of machine learning, right? And many of you would have heard about machine learning in the context of artificial intelligence, and I'm sure there's a handful of you who are very smart, and a handful of you, majority of you who think it's an interesting idea, and some of you who haven't thought about it much. But all machine learning is, when someone says, oh, we're going to machine learn something, is the creation of models. You're creating a model of the world in some way that a computer can make sense of and make decisions with and behave with, right? So you think about Tesla cars, how they can drive themselves. Many cars can do this now. Go away, Bing. Must be the only person on the planet that uses Bing. Not that I use it every day. But, you know, you think about like Teslas and, you know, autopilot self-driving. It's like these cars have a model of the world, right? Like the car isn't looking at the road and saying, oh, that looks like bitumen. It has a world view where it's like, I understand I'm in 3D space. I've got lines here. I've got, you know, direction here, sign there. You know, it kind of classifies everything at a very high level and builds its own conceptual model of the world. That's the framework in which the machine learning happens in. So most models are often concerned with these three things. And my comment before was just that a lot of machine learning is about using the past to think about the future. And you see this all the time with weather, right? Like, let's say you're trying to predict weather. You're trying to model weather, you know, what's going to happen. Well, you might say a few things like, all right, well, if it's really hot today, it's probably going to rain tonight. Like really hot today. You know, I think this is true less so as you go further south in the country, and it's true more so as you go further north. But if you go into like Queensland and whatnot, if it's a very, very hot day, there's a good chance it's going to rain in the evening. So there's a conceptual model right there, a model of rain. What goes into the model? Well, how hot is it today? And then you have an expectation of rain. It's very simplified. It's very conceptualized of this very complex system. Then what you might do is you might go back and look at all the past state of affairs, the last 5 years, and look at all the hot days and see how often it rained. And that'll give you a pretty good indicator. And then you can say, well, we're going to use this to predict the weather. You know, and none of these models are perfect because most conceptual models are high level. They're high level of abstractions. And when you're dealing with complex systems, it's never going to be exactly perfect, as you would know from the weather. Okay. Communicating models, like why do we have models? I've kind of, I guess, touched on this implicitly, but it's like, most of the reason we model things in a conceptual way is because we want to be able to communicate it to someone, right? We either want to learn or communicate. And there's four items here in a more formal sense, like the 4 fundamental objectives of communicating a conceptual model. It's to enhance someone's understanding of something. Without the model, they might not be able to understand it. It's to facilitate, it's very wordy stuff, efficient conveyance of system details between stakeholders. That's essentially saying, let's bring everyone on the same page. Like if we can model something complex, then we can get everyone together to understand it. Provide a point of reference for system designers to extract system specifications, document the system for future reference. Now, I want to touch on a few of these because the third one I think ties into a little bit of what we were talking about last week, which is saying sometimes we model things for you, an engineer, to be able to actually build the system. If someone came to you, some random person came to you and said, I want to build a communication system. Sounds very complex and there's a lot of details there. But if someone can effectively model that for you, if they can put it into a diagram to explain to you how the system works, if they can put the data there so they can say, this is the data we need to capture. This is the state diagram, is in the flow through the program of behaviors. It makes it a lot easier for you to go away and think about how you're going to code it. So a lot of the time, programmers are interested in conceptual models because it's like a good stepping stone to getting to something else, right? It's like having a plan. The first and second one, though, are a little less about the engineering and a little bit more about the communication. The first one's pretty simple. Even in scenarios where you're not building something, and even in scenarios where you don't have stakeholders, sometimes coming up with a conceptual model is a good thing because it helps you understand it better. You know, it just helps you understand it better. You do this all the time probably without realizing it, you know? You plan out a trip. Like you think about if you're going to Europe or something and you've got 10 different countries to go to and all this stuff, you can make a high level of abstraction that kind of links it all together. You know, you could draw some circles and here and write train or something, and it's like they're all different trains in different countries, different costs and stuff, but you're abstracting it out. The second point is like that, but it's a little bit more concerned with other people. So it's like it's saying that models are there to convey information to stakeholders. Okay, what's an example of that? Well, a lot of COVID stuff. Most of you, because you're either based in Australia or you think 90% of you live here. Sorry, 90% not live here. 90% of you are currently residing in Australia, and I think 10% of you are residing overseas. And it's like, you know, whenever you see those COVID briefings every day, it's not like, you know, Gladys Berejiklian and Dominic Perrottet in New South Wales or any other of the premiers. It's not like they're sitting down there looking at the biochemistry of the virus or whatever. It's that they're actually, you know, dealing with a model. So you have like New South Wales Health builds models that actually show you, you know, this is the number of cases and this is how it's projected and these are the different, you know, in community transmission. They're trying to bring it to a high level. So models are predominantly about communication in some way, communicating to you as an engineer, communicating to yourself as someone trying to understand it, or communicating it to many people who are stakeholders in the system. Another example of that was a couple of years ago, I had to build like for lack of a better word, a mini banking system. That makes it sound more dramatic than it is because it's not. And it's like in that, we had to make a model for it, even though the system was really simple and an engineer could sit down and look at the code and figure it out like that. We had to build a model because we actually needed to pass it on to a bank and to other partners who said, we don't know how your system works, explain it to us. And they're not going to accept Python files, are they? You're not going to be talking to a business operator at some other company who says, send me some Python files so I can understand your system. They're going to ask for, well, they're going to be like, can you send me a document? But it's essentially a conceptual model. So, you know, these things matter. I talked a little about this before, like some of these UML class diagrams. You talk about this in 2511. It's a core course, so all of you will. ER diagrams, that's covered in 3311, which is an elective. But many of these diagrams can be broken into two types, which are called either structural diagrams or behavioral diagrams. Now, structural diagrams have a focus on just explaining the static structure of the system. In the meantime, think of UML class diagrams like a diagram that has all of your Python files and just explains the interactions between them. Like, how are they related to each other, right? You know, think about a house. You could draw a house as a diagram of rooms with lines connecting them. You're just explaining the structure of the environment you're working in. ER diagrams are just explaining database design. We're not talking about them today, but if I just Google them, you'll see what they look like, you know, and it'll probably make a little bit of sense because here is an ER diagram that consists of books and publishers and members, and they all have properties, right? Sounds like what you're doing. You got channels and messages and users, and they all have properties. So it's just a way of modeling that. And then class diagrams we're not going to go into. The second type, and somewhat the more relevant type to you because of how it ties into our content though, are our behavioral conceptual models. Behavioral conceptual models emphasize the dynamic behavior. They're not really like taking a snapshot of the system as it is forever. They're more explaining how something goes through the system, explain someone's behavior as they interact with it. We already talked about use case diagrams last week, so hopefully a lot of that is kind of clear. because you're like, okay, use case diagrams, that makes sense. You know, you think back to the example with the bank, and the person goes to the ATM, and the ATM talks to the bank, and the bank replies, and you know, you're explaining this behavior. What's the behavior of the components of the system as it moves through time? So there's usually a sense of like time is passing when it comes to behavior models. What we haven't talked about though is state diagrams or state machines. Now, this is the one conceptual model we're going into detail with today, though in theory you could say that you now know two, which is your use case diagrams and these state diagrams, which are both conceptual models, and they're both behavioral conceptual models. Now, what a state diagram is it's something that represents a state machine. And I remember hearing the word state machine probably when I was like, I don't know, 19 or 20 or something, and it sounded really weird to me. But a state machine, it says state machines are made up of a finite number of states. A state machine is nothing fancy. Don't get lost on the word machine. You could call it a state-based system. It's essentially a system that kind of moves between different states, and most things in the world do this, right? You think about your computer. It's either off, it's loading, or it's on. Or, you know, it's off, it's booting, it's on, it's logged in. And you're just kind of rotating it between those cycles. And you might think, oh, well, Hayden, sometimes I'm doing A and B, but it's like, it depends what you're modeling. If you're just trying to model the state of a computer at a high level, it's really just off or on or booting or something like that. You could model other things like this, like a dishwasher or a washing machine. It's off, or it's like, you know, it's off, or it's on, or it's running back. Anyone who's done electrical engineering, as Alex says, is going to be well aware of these things because, you know, in a lot of ways, electrical engineers deal with state diagrams and state machines a lot more than us. But a lot of things are state machines. And the thing is, most software systems are also state machines these days, particularly anything that's like a long-running application. You know, if you have a Python script that just runs and finishes, it's not really a state machine. It's just a program that goes, you know, go done. Whereas you think about your Flask server, it's actually like a thing and then moves to here. Every time you make a request, you're kind of changing the state of what it is. You know, you're a state machine. You wake up, you put clothes on, you eat, you shower, like whatever it is, you're kind of moving through different states throughout the day. Now, some things are very difficult to model, right? If I asked you to draw yourself as a state diagram, which sounds like a fun activity, really. That should probably be like a lab exercise. I'm going to make a note of that. Not for you. Lab exercise. State machine of a student. Yep. Easy. This is how things are done. So, at its core, though, a state machine is a machine that can be transitioned from one state to another via an action. Don't get lost on the human example here, because we have some simpler examples to explain the concept. For instance, I have a door over there. It's a state machine because it's either open or it's closed. Now, how open is it? Doesn't matter. A conceptual model is a high level of abstraction of this, and maybe a state model might have, maybe a conceptual model might have more detail, but we want to keep this one really simple. So the door's either open or it's closed. And how do you move between those states? Well, you complete an action, right? And then that, yeah, sorry, I'll get to that in a sec. You complete an action. So if the door's closed, you can't close it because it's closed. You can open it, and then it becomes open. And once it's open, you can't open it again, and then you close it again. Edis Ambrose says a script could be a state machine, such as the script's running and then it's running and then it's not running. Yeah, you could. Like, this is the thing about conceptual modeling, is there's no like rules for it. It's like you can model anything any way you want. Some people might call it stupid, but it doesn't stop you doing it, right? So for instance, if you said, here's a script that takes a second to run, and you were like, oh, I'm going to model it as not running and running, be like, why'd you do that, right? But it can be done. Whether it's useful is a different story. You know, in inspiration of, you know, Blake's comment, you know, you could, many of you, I'm sure, could do this. Here's a state machine for you. You're tired, and if you do anything, you're still tired. There you go. That'd be a fun little meme state machine for some of you. You know, if I asked you to draw one for yourself, I'm sure I'd get something like that from someone. Let's go through some more interesting examples. So, well, this one's just kind of touching on this. There's a few bit of, you know, states are circles, transitions are arrows. I think you figured that out already. I'm imagining most of you. There's two circles there and there's arrows connecting them. But like, let's look at a slightly more interesting one. You know, and we're going to look at like a parking meter. But, you know, again, you could do this with anything. We've got user interfaces. Like think about like this entire slide deck we have. It's a state machine. You think about pretty much any website you've used. It's a state machine. Conversational interfaces like streams, that's a state machine too. But let's have a look at a parking meter because I think this demonstrates, you know, kind of like something more complicated. Because the door example's all well and good, right? It's like, oh, the door opens, the door closes. Cool. You know, I feel like you could teach that to a year 7 student. But this one's a bit more interesting. Think about a parking meter. Now, a parking meter is something that I don't interact with much because I don't have a car, but I'm sure some of you park sometimes and pay for parking sometimes. And if you try and model that process, so someone says to you, I have an idea for a parking meter. Imagine parking meters don't exist yet. No one's paid for parking because it's 1970 or something in Sydney, and you know, there's not as many people here. So we say, well, we need to actually model parking. And then you say, I've got an idea, it's called a parking meter. And someone says, what in the world is a parking meter? So you go away and you say, I'm going to come up with a conceptual model. You probably come up with a few other things. I'm going to come up with a conceptual model for a parking meter. And you come back with this. And this is a high-level explanation that helps stakeholders understand it and probably helps engineers understand it as well. So what is that? Well, you start off by you enter the parking bay. Great, what can you do here? There's 5 lines, but only one of them is leaving, so there's only one thing you can do, which is that you can input the number of your like parking bay. So you know, I'm in parking bay 3. Once you've entered your parking bay number, you get asked to enter the duration that you want to be there for. Now again, there's 3 lines, but 2 of them go out. So from here, you can either cancel it and go back to the start, or you can input the duration and then you get to the next one where it says, please insert your coins to pay for it. Now again, here there's 4 lines, right? But there's 3 out, which is you can either cancel it at this point, or you can start inserting coins. And as you insert coins, it's either going to send you back here because you need to insert more coins, or you're going to have sufficient funds and it go to the confirm and you're done. Once you're on the confirm though, again, you can either cancel it or you can say, yes, I want to pay for it. So it's really just trying to describe all the different behaviors through it. You know, it's kind of like a use case diagram, except a use case diagram is not really concerned with a sense of system states. So in some ways, this is more technical, even though they're both, you could argue, do a somewhat similar thing. You could imagine that this is a lot better as an engineer. Like a use case diagram doesn't really, like it's useful for an engineer, but this really describes a system. And like this is probably like one of the most common types of diagrams that I think you would ever try and conceptually model, because it's like you could take this and build something. Like it's nearly like a set of requirements for a system in some ways. And occasionally when we talk about this, there'll be a student who says, oh yeah, I get this, but isn't it a bit weird? Like it says insert coins and all I can do is insert coins or do sufficient funds. So it's like, what if it's a $2 parking and I put in $2? I'm not really doing an action called sufficient funds. And if I inserted the coin, I end up back here instead of finishing. And it's like, again, it's a high level explanation of things, you know? Like this doesn't take into account things as well about what happens if, you know, the machine has an error and it can't accept the coins. There's some things you could add here. Should you complicate the model, or should you just say this is a simplified model? Well, that depends on what you're trying to do, but both of those are possibilities. And, you know, this is an example of us kind of padding it out a bit with a bit more information. In this case, we've got our, like, for lack of a better phrase, we've got like an auto cancellation going on here, where we can say, well, if they're at enter duration, or they're at insert coins, or they're at confirm, after 5 minutes, we will reject it. Now 5 minutes is a long time, to be fair. It's probably more like 10, 20 seconds or something. You don't want someone thinking they paid and then, oh, you'd imagine that, right? Someone gets to the confirm screen and they think I'm all good, and then they walk away, and then 5 minutes later this machine starts crapping coins out to some stranger. So a lot of thought goes into system design. Can we model the Opal card as a state machine? So if you think about the Opal card, I mean, or your credit card, whatever, but Opal card being a Sydney-based thing, it's kind of weird with everyone online now, because there's like literally students doing this course that have never had to like use Sydney public transport before, which is quite an interesting thing, because that's where all the examples come from. But I mean, how would we model an Opal card, right? Like, you've got an Opal card, and it's essentially a state machine if you think about it, right? So like, what kind of states do you have in an Opal card? Well, Paint's a terrible tool for this, by the way. I probably wouldn't normally use this. You've kind of got your what would you? It's not even. Let me grab something else. Why is the internet so slow? Maybe we'll have to use Paint. Damn it. Okay. You think about an Opal card, it's like, well, you have what kind of states do you have for this thing? Well, you kind of have like an untapped state, right? Where your car's just like sitting there doing nothing. And then what happens? Well, you can go to, say, a train station and you can tap it. And like, what happens when you tap it? Well, if you tap it, then you're like, now let's just call it like tapped on. Okay, well, what happens between there? Well, you kind of, you tap. But how could we draw this? Well, we could say, you could say tap with sufficient balance, maybe? And then you think, well, what happens if it's an insufficient balance? You just kind of say, come back here. It's like it's untapped, right? You try and tap on, but you can't. So it's still like untapped. You haven't tapped on. And it's like, okay, well, you tap on. Now you're on some kind of, train. And eventually at some point you're going to tap off. And when you tap off, what's going to happen is that you're going to get, some kind of, say, information about, your new balance. You've seen that like on the old Opal card. No one probably uses them anymore because everyone's using credit cards, but like, you have like your balance info. You tap off at a train station and it says you got $2 or whatever remaining. So when you tap off, you get this. And then what happens after you get that balance info? Well, we could say that we go all the way back to untapped, which is, say after 1 second. Now, the thing about state diagrams is, if you actually think about this, when someone probably drew something like this, and it was probably more complicated than this because they had to take into account a bunch of other things. For example, when you tap off and you get your balance information, you don't actually, like, even though you end up here, it's not so much that you go back to the untapped state. If anyone's kind of used the Sydney public transport before, you actually have this period of an hour whereby if you tap on again, in that hour, you're on like the same journey. So you tap off, you get a balance info, and then if you, or I could even, do something here, like you say, well, when you tap off, it's not so much that you get your balance, it's that you're actually in like a mid part of the journey. So let's call it like, mid journey. And that's where you have that 60-minute window to tap on again. Because if you tap on again in that window, it's kind of like counted as the same thing. So from here, you might then, like tap on. And it's like, cool. Well, you've tapped back on and you're in that kind of state, and then you do that for a while. And there's all these other rules that exist around, if you've been tapped on for more than 5 hours, you automatically get tapped off. And if you tap on whilst already being tapping on, you kind of get charged as well. And you can kind of feel like if you're actually sitting there thinking about it, as opposed to like, being half asleep, you can kind of feel some of the confusion or tension with this, right? So for instance, if you have a card, like let's say you tap on a bus and you don't tap off a bus, and then you go and tap on a train, you got your Opal still sitting there thinking that you've tapped onto the bus. So you're actually tapped on now, and you've just tapped on again. It's like, how do you handle that case? Well, you actually get kind of charged more in that case. So then the question becomes, well, how do you represent that? Like, how do you represent a fee in this kind of diagram? Because is a fee a state? Not really. Like, you don't really like move from tapped off to tapped on to fee paid. Or maybe you do. Maybe you do what we had before, where you say, you tap on and then you tap off and you get a balance, or you get a deduction, and then after 1 second you automatically get sent back. That's like probably the way to think about it. The way I would try and conceptualize a state diagram for Opal is, again, if you tap on, I'll just pull this up because I'm sure there's like 5% of you that haven't, seen this. It's like, you have this little machine here. I would try and think about, the state of an Opal card by this kind of tapping machine here. Because if you actually think about it, the state of your Opal card only ever really changes when you actually tap on those kinds of machines. So, you move from these different kinds of states. There's another rule, for instance, with Opal, where if you tap on, but then within 15 minutes you actually tap off, they refund you. So there's actually a scenario here where it's like, it's not that you go from not tapped to tapped on to tapping off in your mid-journey. If you actually tap off within 15 minutes, you go straight back to untapped. There's no fee to be paid, you're not on a journey. So maybe you need to split this diagram up, right? Where you actually say, well, if we get rid of all of this for a second, you say, well, when someone actually taps on, they're in like, some kind of 15-minute grace period where, if they tap off in that time, they go back to untapped. But if they don't tap off in that time, then they kind of go into this other category, which is like, 15 minute passes. They go into this other category, which is like tapped on. So it's a difficult task. And like when I talked to you all last week, I said something to you along the lines of like, everyone can program. So stop, don't feel special because you can write code, because again, there's millions of people who are doing that for cheaper. You need to start thinking about your value in the world of software as someone who can effectively do this. Because I guarantee you, if you're someone who can like sit down and draw something like this and represent a system and have a conversation with someone, both the people, say at Sydney Transport trying to design the system, and also, like a lead engineer or a team of engineers, like that is where you are your most valuable as a communication conceptualization asset. And that's why this topic is so exciting to me, because it's so much more important than Python and Flask and all of that. So we do a little bit of this in the project naturally. We ask you to draw one to describe your new features, So if you have a new feature like I don't want to say any, because then, puts you in the position where either you just do it, or if you've done it, you feel like you're doing it because you were told that it was a thing. But there's a chance to try and draw your own state diagram for that and share it with your tutor. Now, in the last 15 minutes here, I wanted to talk about a different kind of conceptual model, which I think is really interesting, and it's something that I was involved with, which means I can talk about it with some interesting detail, which ties into a little bit of what we were going to talk about last week, but I said we'd run out of time. So, when we talked about conceptual models, we've said that a lot of the time, they're going to be diagrams. We talk about use case diagrams, state machines, even the ER diagrams and other stuff I showed you are all diagrams. They're all visual stuff. But an example of a conceptual model that's less visual is a tool that was written as part of the SunSwift team. And that tool was called Galleon. And I just want to really step through this as an example of how someone used Python, which is also why it's topical, to actually build a conceptual model. So this isn't always just diagrams and lines and stuff. Sometimes this is actually about writing a lot of code, and sometimes models are just a lot of code. So here's the problem. I'll really contextualize the problem for you quickly. So this is kind of a bit of, I say fun, it just means that, like you're not going to get an exam question about some specific detail of this. It's really just to drive home the point. There is a race every 2 years between Darwin and Adelaide in Australia. This race is called the World Solar Challenge. There's going to be a map of it somewhere if I scroll down far enough. or I get lucky, which I didn't, there's a race like this, and you start in Darwin, you drive to Adelaide. There's about 45 different teams around the world. They are made up across, I don't know, like 15 to 20 countries. There's like 5 teams from Australia, and there's a few from the Netherlands, and there's like 5 or 6 from the USA, and a few from Germany, and then all over the place, right? I think there's 2 from Japan and everything else. This shirt is from a South African team from northwest of Johannesburg, right? And this particular challenge is like, you start here, you drive here, and you have 6.5 days to do it. So if someone tries to explain this to you, it's like, you know, if I was just explaining this to someone, I'd say, well, yeah, it's a pretty simple idea. You all start up in Darwin, and you have a day. And, you know, that day basically goes from 8 a.m. to 5 p.m. And this is the window in which you can drive a solar car from Darwin down to Adelaide, right? You have a window like that. And then you have a bunch of days to do this in. So, you know, you've got like day 1, you've got day 2, you've got day 3, like this. You can't drive before 8, you can't drive after 5. There's a whole bunch of little rules in this, like you can start driving, you can finish driving between, like, if you finish driving at 5:03 p.m., then you start the next day at 8:03 a.m., you know, and all this. But again, the whole point of a model is not to worry about all these details. It's to try and explain this at a high level. And this kind of goes on for a while, and you have all these different days. But then within each day, one complicating factor here is that every time you hit one of these red markers on a map, which are all different kind of towns, if you will, or literally petrol stations, you have to stop, and you have to stop for 30 minutes. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. We call these things, or, well, we don't call them. They're called control stops, and there's 9 of them, and they're 30-minute stops. And you hit this when you hit it. So let's say you're driving from, you know, Darwin, where you start on like day 1. You're at Darwin here. You might hit the first one, Catherine, at about, well, typically you'll hit it around 2 or 3 p.m. on the first day. So you actually need to come to a stop for 30 minutes. Why do these stops exist? A whole bunch of reasons: safety and giving the officials a chance to make sure everything's going okay and check in with teams and all of this stuff. So there's a whole bunch of layers for it, but you know, you'll be driving for this entire time here, and then you'll take a 30-minute stop, and then you'll be driving for this amount of time until the end of the day. And then on the next day, you might have another stop. And on some days, you might have 2 or 3 stops, you know. So then you have a stop here on the next day, and then a stop here. And these are all 30-minute stops. Now, again, I mean, I might just bring this down a bit so it's a little bit simpler, because we don't have much space. But, you know, you have all these different days here, right? And you've got your 6 days, and it's pretty simple. It depends on the particular year that the race is happening in, but let's just use 2015 as an example. That year it was who can get there first. You know, so everyone's got the same stuff. Everyone's got, you know, everyone's got a 60-kilogram lithium-ion battery, right? And you have to get there first. And you have to figure out how fast to go. And this is the hard part, because the thing is, when can you charge your car up? Well, again, there's all these different races with different rules, but let's say in this one, you're allowed to have a full battery right here. And when you got to Alice Springs, in the middle here, you were allowed to charge, let's say you get there like, you know, here overnight. You're allowed to charge up your battery then. And everything else in the meantime had to come from the sun, you know, because it's a solar car. And the question is, how do you get to Adelaide first? How do you beat other teams there? Well, you need to go fast. But if you go too slow, you're going to lose. If you go too fast, you run out of energy. Because if you run out of energy here, for instance, you're going to be sitting on the side of the road for a couple of days to get your energy back to actually be able to drive that far. So it's a very fine line. Now, how do you figure out what speed to go? Because that's essentially the problem. It's like, what speed do you do? Well, that depends on a million things. Depends on, like, literally so many different things. And that's the question that motivated a series, you know, essentially the conceptualization of this. And it started a long time ago. because various people did this over the years. There was some research done by an older UNSW student, Alex Bulgakov. They wrote a whole. They did. I don't know if they did a thesis on it. I think it was their undergraduate thesis. I can't quite remember. Oh, Gernot. Wow, I didn't know they did that with Gernot. There you go. That's really nice. So, you know, they did this whole thesis on it and talked about all the different, you know, dynamics. Oh, there's the damn map. The dynamics of a car. But then in 2015, there was another UNSW student who actually tried to make their own conceptual model, and that model was called Gallium. And what that model was trying to do was pretty simple. It was trying to figure out what speed to do, right? What speed do you do at any given time? Let's just think of it like every 1 minute, you have to ask yourself, what speed should I be doing now? Just the right one. And to answer that question, you need to have a model of this system. Because like if I said to you, figure out every minute I want you to tell me what speed to do, you'd be like, I have no idea. I have no idea, right? So like have an idea, develop an idea. And what ended up doing was we had someone who was a UNSW student. They made a model which was essentially something that took in a bunch of inputs and helped you get an output roughly. Now, the particular race that was interesting here wasn't so much that we had a 60 kilogram battery. I don't want to complicate it too much, but it's like the model that came up with was essentially a Python program. It was actually built like a state machine that tried to take all these different elements into account. Because if you think about it, if you're a car driving on the road, what are the things that affects what speed you do? Well, if you think about it a different way, the speed you do is going to be based on the amount of energy you use, right? You get this. Think about a race, right? You're a human. You've probably run 400 meters before. Maybe you're really fit and you've done like a marathon or something. If you run too slow, you lose. If you run too fast, you're gonna fall over and die, right? So it's like, how fast do you run? Well, you want to run at the same speed ideally, right? Because you know this from running or cycling. If you go really hard then really gentle and really hard, you're going to get really tired. So you want to be consistent. How consistent do you have to be? Should you go faster down hills? Should you go slower up hills? You know, when are you going to take a break? All of these things kind of matter. So what are those things that affect it? Well, you have the wind speed. This is, you can model most of this stuff the same as you would a human. It's like you're driving along and the wind is blowing. How hard is it blowing? If it's blowing from behind you forward, then naturally you're going to get a kind of boost. If it's blowing in front of you backwards, you're going to get some kind of, being pushed and slowed down. What direction is it coming from? The wind can be blowing really hard from the side, which is, well, I just kind of mentioned direction before. How much energy is the sun putting out that day? That kind of varies a bit. The cloud cover also changes that. If there's clouds, you get less sun. But also, sometimes a few clouds will get you more sun than days without clouds. You've got what elevation are you at? Are you going up a hill or down a hill? How fast do you want to go? How is your car oriented with respect to like north-south? Because, if you have a car, because, a lot of these cars aren't really sitting there as flat, right? A lot of them might look like this. So, if you have your solar panels over here, then you think about what the sun in Australia is doing, right? If you're driving south, right? If you're driving south this way, where's the sun in Australia? A lot of the sun in Australia is kind of up here, shining down in this direction. So where you are on a map, how you travel changes, So for instance, you look at a map like this. It's like when you're traveling kind of southeast like this, you're not going to be in the the ideal direction and so forth. So all of these things kind of matter. And what the student did was they built a conceptual model, and they built a conceptual model that broke the entire 3,000 kilometer race up into a series of segments. Think about it like, a 200 meter stretch, a 400 meter stretch. And in each of those stretches, they fixed all of these inputs. They said, yep, in this little 200 meter stretch, the road's like this. We expect the wind to be like this because this is the prediction that the Bureau of Meteorology gives. We expect the solar output to be like this because, Weather Zone says it's going to be like this. We expect, the weight of the vehicle to be like this because we know that weight. We know what the orientation is because we know what the road's like. And then we're also going to have, we can pick a speed that we want to do and see how much power that uses. So this entire, race was conceptually modeled as a big series of intervals. So those intervals, you know, again, would just be like, think of it like, it's like sampling, right? Like sampling music. You might have learned about this in high school physics. You know, sound, analog to digital. Chart, I don't know if I'm going to get lucky. You know, you think about sampling, right? Like you have your natural environment that you need to model in a more discrete fashion. So that's kind of what happened. Was this student took that. So let's take this very complicated race, break it up into segments, and then for each segment, let's make it static. Let's say that the wind's only this fast in this segment, and the wind's only this fast in that segment, for instance. And then let's just like sum them all up and see where we get to. So you can imagine that a system like that, if you can kind of say, well, I've written a model, which is basically a Python, think of it like a giant Python function, but it's far more complicated than that, that takes in all these inputs and spits out an energy usage. I can play around with that speed because the slower I go, the less energy I'm going to use. And you can use that to essentially kind of like channel it all back together to get to like, you know, some kind of final point. So that was an example of, that's an example of a programming conceptual model. There was some basic charting with this, but a lot of this model was actually a command line interface. It was actually a program that was written in Python that you would interact with on the command line. That model was used for 2 years. It was a very interesting model. It was something I ended up working on, which is why I'm familiar with it. I didn't write it originally, but really interesting stuff. And yeah, that was about it. It was to figure out, you know, in the 2015 race, the question was actually like, you have a 60 kilo battery. Figure out what speed to do. And the 2017 question was a bit more complicated. It was that you're going to be driving at an average of 62 kilometers an hour. Figure out how much battery you need. That was the question there. You know, and again, because we had a model, so this was like the 2015 UNSW student wrote that one, and this one was 2017, which is what I mainly spent time on. It was like we already had a conceptual model of it. So if you look at like the amount of work that was needed in that second one, it was very small because we had a model for it that could communicate and be worked with. So, you know, it was very powerful that way. Josh says, why do you have a battery for a solar car? So the fundamental problem with solar energy is that its output is very low. So if you have a square meter of sun, like this is a square meter, right? 1 meter squared. The sun, literally the sun, if you capture that entire amount of energy, it's about 1,000 watts or a kilowatt. It's about, you know, it's about what the energy of half a toaster uses, right? So if you just want to power half of a crappy Kmart toaster, you probably need the entire energy output of the sun as it hits the earth across a square meter. The problem is that, you know, most of our solar panels we have at the moment are only about 25% efficient. So that means that you're only getting like 250 watts of power, which isn't much at all. Like, you know, if you think about a Tesla as a car, a Tesla will put out, if you like hit your foot to the floor and, you know, you see all those videos on the internet where someone's like, in a Tesla, those cars use about 550 kilowatts or 550,000 watts of power. So the whole problem with solar, and as a general rule, because solar cars don't make a lot of sense, is that the amount of energy you get from the sun is not only small, but it's somewhat capped. Because you can't just like, you can't really go above this number. Like, not without getting into reflectors and stuff, right? Like, you can't just ask the sun to put out more energy per square meter. This is the problem with solar. Back to your question, why do you have a battery? You have a battery because you need to store this stuff. Because ideally, you need to store it up because when a car's driving, it's going to use a lot more than you'll ever be able to get from the sun at any given time. And in fact, you know, these cars, which are, you know, they're worth about $1 million. They're worth about $1 million, $500,000 to $1 million. And it's like these cars here are very light, very, very efficient, very expensive, and they'll typically use cruising. They'll use like 3 kilowatts, right? And on their roof, they'll have, say, 5 square meters of solar cells that are all pulling in 250 watts, which means that they're getting, you know, 1.25 kilowatts in or something like that. So even these insanely efficient cars are still using more than they can get from the sun. So, you know, that's why you need a battery, because there really is no scenario out there where you'd ever have a car that's just running off the sun. Even if it was sunny all the time, it's just not, the physics don't check out, basically. Pretty sure even if you just strapped a solar panel to your head, I mean, like, it'd have to be a bicycle or something. Anyway, let's take a break in a few minutes. I wanted to see, I mean, that was a bit of a deep dive. I wanted to spend time doing that because I think we touched on a lot of really high level concepts in this course, and wanted to kind of talk about, you know, something more, I guess, in depth. But again, just to recap, this was a Python program that literally like took in numbers. So you would say something like, I'm making this up a little bit, you would actually just quite literally on the program run something like, you know, Python 3 gallium.py, and then you might, you know, specify the distances you want to go. Like, can you tell me what speed I need to do between, you know, 100 kilometers south of Darwin and 102 kilometers south of Darwin, like this. So you give it 2 command line arguments, and it would be storing all the data, and it would kind of figure it out, because you know, a lot of this stuff is just maths. You know, for instance, how much energy do you lose to these various things, right? And to talk about conceptual models again, it's like, it's really interesting because there's things you can model quite easily, right? So for instance, in a car, you have like 2 main energy losses. Forget the solar car for a second. All on a flat. You're driving a standard car on a flat. There's no sun. It doesn't really matter. There's 2 main things you're competing against, right? You're competing against essentially your mechanical systems, your mechanical drivetrain, and you're competing against the air, right? The first one is you've got friction in the tires, you've got friction inside the engine actually turning, right? Because there's heat losses, right? Like, why does your engine in a car get hot? It's because that's energy you're consuming that's not being, you know, transferred out to the wheels, and then you've got the air you're pushing back against. And typically, for instance, a mechanical drivetrain, the amount of energy is it the energy? I think it's the energy. The energy you're using it's proportional to the cube of your speed, right? Whereas like, wrong one. The energy of your drivetrain is proportional to the speed you're doing, and the energy loss in the air is proportional to the cubic of your speed. So what that means, and you know this as a person, if you've been on a bicycle or anything like that, if you're moving at 1 kilometer an hour, which is about, you know, 4 times slower than a human walks, you're not spending any energy pushing yourself through the air at all. Whereas like, you're spending most of your energy actually just trying to, like, you know, move the systems. But when you go really, really, really fast, it's the other way around, because, you know, as you get faster and faster, it actually, like, kind of, I don't want to say exponentially because that's mathematically wrong, it cubically, but exponentially gets like more difficult. So this is all stuff you model. We talked earlier about mathematical models. Well, you go back to Alex Bulgakov's thesis, and I haven't looked at this in forever, but it's like, here's a model. This is quite literally what I've just talked about, I'm pretty sure. You have this is your mechanical losses of a system, and this is your aerodynamic losses of a system. You can actually see it there, right? You got your velocity cubed, and there's just your velocity not cubed. So this is all how you describe systems. Now, granted, this is something you wouldn't do much in like the general software space naturally, but you know, I'm sure there'll be one of you here who goes and works for Tesla one day. You know, you end up working in the, you know, predictive driving team, where the team tries, like, how do you think Tesla figures out what range you're got left in the battery, right? It's not just like that they randomly pick it. They actually will, you know, look at things and have a mathematical model based on this kind of stuff. Anyway, that's all. Let's wrap that up. That was a fun little deep dive, and let's take a break, and we'll get started again at 11:10 and get stuck into it.